All right, so welcome to video number 6 of my Calculus 3 Intro to Mathematica series. In the last video, we started our introduction into vectors, and we primarily focused on the vectors that only have numeric values. In this video, we're going to continue talking about vectors, but now we're going to move into the idea of vector functions. So our vectors are going to have particular functions involved that you're going to learn about during lecture, and then you can now show you how to apply this within Mathematica. So let me share Mathematica with you. And so today, the first thing I want to do is make sure we are comfortable defining a vector function. So we learned how to define vectors with just numbers last time. So how do you do this with an actual function? So kind of combining what we did in the last video with what we did in earlier videos, if we wanted to define a vector function, let's say r of t, so we would do r of t underscore. Remember, you want to do the underscore anytime you start to use a new variable, a new function. That way Mathematica knows you're about to define it. And since this is going to be a vector function, we're going to use our open braces, which is how we define vectors. And let's use this one as an example. Let's use t as our first element. Our second element, let's use 1 divided by 1 plus t squared. Excuse me. And for our third element, let's just do t squared. And so you can see we're defining it very similar to how we defined functions back earlier in earlier videos, but now we're going to actually put it in as a vector. So if I enter that, shift enter, we now have our first vector function defined. Now, one of the things you're going to want to be able to do first on some of your project problems is to graph a vector function. So as you've learned during lecture, vector functions are treated very similarly to parametric equations. So we're going to actually use the built-in parametric plot function to help us graph this. Now, the biggest difference between what I taught y'all in a previous video and what we're going to do here is that this is a three-dimensional vector. So when I go to type in the built-in code parametric plot, you'll notice that this one, which is a little bit different from the one we did back on video 3, this one has a 3D on it because it's telling you it wants to graph it in 3D. So if I click on that and click on our double down arrow, we're just going to use the first one here to make it a little bit easier. So I'll do that right here. And what you should be able to do is, instead of listing them all separately, because you're more than welcome to type all these out again, but what we should be able to do is just to delete these, and we are just going to use r of t as our overall vector function in this case. So if I do that, and then I do my parameter is t, and let's say, let's go -5 to 5, -5 to 5. And let's see if this will graph what we have here. And there you go. There is your vector function. Now, similar to the quadratic surfaces that we did in the last video, you can take this vector function and you can float it around. Now, like I told y'all, Mathematica does not draw the arrow on here for you, which is perfectly fine, but it does draw it in a three-dimensional sense. Remember that if you need to edit the parameters here a little bit, so let's say I wanted to go from -3 to 3 on the t values, we could do that and it would adjust the graph for us here. So whenever you want to graph a vector function, especially a 3D one, make sure you define your vector function and then you will use parametric plot 3D in order to do that. All right, so outside of that, what I really want to show you about vector functions is the different things that you can do with them. Now, during lecture, we have talked about many different formulas that are applied to vector functions, and I want to do a few of those with you here. So let's start off by defining a new function. So we've already done r of t. Let's use a new letter. Let's just start from the beginning. Let's do a of t. So I want to define a vector function a of t. And for this one, let's do the vector t. We're going to do e raised to the -t. So remember from earlier, we're going to use capital E XP for e. And then we're going to do t times e raised to the -t. So t, e to the -t, and then t times e to the -t. Let's let that be our new vector function. All right, so what I want to do here is we want to find the length of this vector function. All right, so if you go back to your lecture material to find the length of a vector function, it is very similar to what we did back earlier in video 3 when it was 2D, but now we're going to treat it as a 3D parametric problem. So that means that I would like to do a definite integral, and let's do the interval from 1 to 3. Just made that one up. And when it comes to your formula in this case, two things you would have to do here. What you're trying to do is do the square root. And typically what you want to do is take the derivative of each element and add that together. Now, one of the issues is that to take the derivative of this, all right, we are going to typically try to do, all right, I want to do a prime of t, and I want to square this. And then we want to integrate this with respect to t. Now, that is what your first idea is going to be. Now, I want to show you what might happen when you do the code this way. You'll notice that it's spitting out another vector. But as we know, you should not be getting a vector answer when you're trying to find the length of a curve. It should be a singular scalar when all is said and done. That's because the way that this is coded, which is what a lot of students do by accident, all this is doing is taking the derivative of each of these elements, squaring them individually, but it's not adding them together like you need it to. Instead, it's just evaluating each part separately. So we're going to have to adjust how we do this a little bit. So in order to take the derivative and get the magnitude of it in this case, right? So if you want to square each element, what you will have to do is you will take the derivative of A, and we are going to dot that with the derivative again. So we're doing it this way. We're using dot product as our way around Mathematica, not understanding what we want it to do. Because remember from your idea of dot product, what that is doing is it is multiplying each first element times the first element of itself, which is essentially squaring it. And then the dot product allows us to add them all together. So this is the backdoor way to get around actually finding this. So if I just change it from a prime squared to be a prime dotted with a prime, you'll notice, let it run for a second here. All right, it gave you an answer. This happens periodically. Essentially what Mathematica is telling you here is, oh, that's great. I don't know how to integrate this. That's okay. It means it could not find an exact answer, which does happen from time to time. If it gives you an exact answer, great, you're done, move on to the next idea. But if you get this output here, all you need to do is go back and use our old reliable of n%. And what we're going to tell Mathematica is, yes, we know you can't find the exact answer, but can you find an approximation? And it can. The answer is about 2.04537. That is not an exact answer, but that's the best approximation it can get by using the different built-in codes that Mathematica has in its storage base. So when it comes to length of a curve, you're going to integrate, but once you have defined your vector function, all you have to do is take the derivative, which is part of the formula, and you have to dot it with its own derivative. So there's length of a curve. The next thing I want to do is look at what we call, I believe, curvature is the next thing I want to do. So to do curvature, let's do a new function so we can practice. Let's do b of t this time. So for this function, it's going to be a little bit longer, so just make sure if you need to pause the video, do that. Let's let our first element be t squared. We're going to let our second element be sine of t minus t times the cosine of t. And I'm going to let my third element be cosine of t plus t times the sine of t. It's a little bit longer, but I'm setting this up for another reason for an error that shows up once in a while. So here is our b of t function. So now I would like to find the curvature of this. So as you might remember, curvature, there is a formula from class that we went over that talks about that you need to find the cross product of velocity and acceleration, take the cross product of those two things, and then you got to find the magnitude of that. That's your numerator, and the denominator would be the magnitude of velocity cubed. Instead of doing all of that at one time, which you are more than welcome to, I'm going to do it in pieces to try to make this a little bit easier. For example, I want to find first the cross product part. So the numerator of curvature asks us to take the cross product, right, of your velocity and your acceleration. Well, as we know, velocity is the first derivative of b in this case, and acceleration would be the second derivative. So I want Mathematica to find the cross product of those two derivatives with each other. So let's have Mathematica do that first. Okay, so it found that value. The next thing you want to do is you want to have Mathematica find the magnitude of this. So I'm going to have Mathematica find the norm, which is, remember, that's the code for Mathematica, and I'm going to do the percent symbol. Now that I've already had Mathematica do to do the cross product, I just need to find the magnitude. So let's do that. Uh-oh, here's the issue. Sometimes in Mathematica, you will see this ABS function show up. Essentially, what that is saying is Mathematica is trying to remind you that while there are negatives involved in the function, when you actually work this out and you start plugging numbers in, you have to ensure that there are positive answers involved. So since I'm not evaluating this just yet, Mathematica doesn't know that I will eventually put appropriate values in. So I've got to now convince Mathematica that the ABSs are not needed. Here's how you will have to fix this. It's kind of a weird way of doing it. Go back here to your cross product. Since this was the value that we found the magnitude of it came out to be an issue, it's similar to up here where we're going to have to do a backdoor way of doing this. So what I'm going to do is I'm going to start here and I'm going to do my square root function. I need to have Mathematica do magnitude kind of the backdoor way. So what I'm going to do is I'm going to take my cross product value, because I already know that this works based on the output you see here. I'm going to plug that in first. I want Mathematica to take this and I want it to dot with itself, because I'm trying to force Mathematica to do magnitude without running into the issue here. So anytime you run into this ABS issue, it usually happens on magnitude. You can get around this by doing the square root, taking what you were taking the magnitude of. I want to take the magnitude of my cross product, so I'm going to do that. And you'll notice, and you can match the formulas up. The only thing this is going to do is it's going to drop off the ABS values, which might cause a little bit of an issue. So that would be the numerator value of your curvature. For the denominator, you need to take the magnitude of velocity and cube that. So we know that magnitude is found by taking the norm of velocity. All right, so for us, velocity would be the first derivative of b. And I want Mathematica to cube this. So this will be the denominator of my curvature formula. You'll see once again that it runs into that ABS issue. So I'm going to have to use the exact same backdoor plan we did a second ago. So I'm going to open my parentheses, and instead of doing norm, I've got to bring back in my square root, and we are going to take b prime of t and dot it with itself. This way it will find the appropriate magnitude, but I still have to make sure I cube it. So I'm just changing this norm piece to be the official backdoor definition of the square root of the dot product by itself. And you'll notice it should be the exact same formula, only it drops the ABSs off. That's a little tricky way to get around the ABS. If you don't have an ABS, don't worry about this. Just use the formula directly. But I wanted to make sure I showed that because it does show up on at least one problem on your project. Now, as far as curvature goes, I can now set up my curvature formula. So I want curvature, which is usually done as k. We're going to define a new function. It's going to be a fraction. In the numerator, and here's where copying and pasting helps. I can take the first value that I found and put that in my numerator. And I can take the second value, which is this one, copy and paste it into my denominator. And I now have a curvature function. It's very ugly. But typically Mathematica or my project will ask you to find curvature at a certain value. And now that I've gone through the work of finding curvature, I can just have Mathematica evaluate curvature at the value that I want. So in this case, since it's a trig problem, I just picked pi over 3. So what is the curvature, now that I found it, at pi over 3? It would be 3 over 5 pi. And then, like I said, if you need to get your numeric approximation, that's about 0.190986. And so curvature is one of those ideas where usually the ABSs will show up. Just make sure that as you go through your formula, if you run into an ABS, it's okay. Just take what you were trying to find, which is usually a magnitude, and you're just going to take the square root of whatever you're trying to find the magnitude of dotted with itself. And that will fix that ABS issue. The last thing I want to show you for this video is one more application from vector functions, which is unit tangent and unit normal. So we're going to define one more function here to work this out. All right. So let's do, we did AB, let's do C this time. So C of t, let's define this as the vector function t. Then we're going to do 1/2 t squared, and then just t squared. Oops, sorry. So see, I messed up. I put a question mark by accident, so let me delete that and re-enter it. Like I said, slip of the hand there. So we want to find the unit tangent and unit normal vector functions of C of t. So if you go back and look at your lecture notes, first thing we want to do is we want to find unit tangent. So I'm going to call that ut of t. Now you'll notice that I'm calling this a brand new function because you're going to have to use unit tangent to help you find unit normal here in just a few minutes. So what I know from my lecture notes is that unit tangent is defined as taking the derivative of your original function. So I want to find c prime of t, and I want to divide this by the magnitude of itself. So we would find the norm of c prime of t, and that is your formula for unit tangent. But I believe we're going to see the same issue we just finished talking about. You get a bunch of ABSs because when you started to do the magnitude here, it didn't know, it wanted to make sure you were aware of this restriction. We've already learned how to fix this. Instead of doing the norm of c prime, I can now go back up and we're going to delete this. And the backdoor way of doing that is to take the square root and whatever you're trying to take the magnitude of, just dot it with itself. So I would take c prime of t and dot it with itself. And so you'll notice this should be the exact same answer, except all those ABSs should go away, which they do. You now have your unit tangent function. That's all it takes. And now that you have unit tangent, you can use this to help you find unit normal. So for unit normal, we're going to do un of t, right? And so the formula for unit normal is the derivative of unit tangent. So I have to do ut prime of t divided by its magnitude, which is the norm of ut prime of t. So I'm taking the derivative of what I just found and I'm dividing it by its own magnitude. And so when I have Mathematica go to find the unit normal, oh no, there's those ABS values again. Okay, so once again, we can fix that. We just can't use the norm here. So I'm going to delete that. We're going to do a square root, and I'm going to take the information that I'm trying to find the magnitude of, which is ut prime of t, and I'm going to dot it with itself. You should get the exact same answer, except all these ABSs should go away. So let's do that. And there you go. It's a pretty ugly answer, but this would be your most simplified unit tangent vector, or sorry, unit normal vector you can get. Now at this point, if I'm asking you to evaluate it at a certain value, you can do that. So if I wanted to find the unit tangent value at 1, I could say, what is ut of 1? It would be 1 over root 6, 1 over root 6, root 2/3. Or if I wanted to find the unit normal at 1, we could do the same thing. Now you'll notice on one like this looks pretty complicated right here. So this might be something where, okay, maybe I need to get a decimal approximation if that's something that's needed. Now, if the project just says find an exact answer, this is perfectly acceptable. That's fine. But if you do need a decimal, or if the problem asks for a decimal, just don't forget our favorite code, n% will give you a decimal of the previous output to get the approximation. And so in this video, I introduced the idea of how do you define vector functions in Mathematica. We talked about how to plot vector functions in Mathematica. That would be using the parametric plot 3D. Excuse me. Then we also talked about a few applications of vector functions. I showed you how to find the length of a curve, or length of a vector function. I showed y'all how to find the curvature of a vector function. And I also showed you how to find the unit tangent and unit normal of a vector function. Biggest thing, especially on those last three, curvature, unit tangent, and unit normal. If you run into ABS in your output, that is okay. Make sure to go back to the code that you just did, and instead of doing norm, you need to do the square root of whatever you're trying to find the magnitude of dotted with itself, and that will fix your issue. That puts a wrap on video number 6. In the next video, we're going to actually wrap up my introduction to Cal 3 Mathematica. We're going to move away from vector functions because the last topic that I need to cover is Taylor series and Taylor polynomials. I'll show you how those work in the next video, so I'll see you then.